Hello everyone, welcome to my presentation. My name's Khalid Abdallah, and this presentation is on the impacts of advancements in AI on the cybersecurity field. Alright, to begin, the contents of this presentation will is mainly on the transformative effects of artificial intelligence on cybersecurity. We begin with a compelling problem. While AI equips defenders with powerful tools, it simultaneously empowers adversaries to craft more sophisticated threats. From this duality arises a series of research goals that aim to dissect the technological, practical, and ethical dimensions of AI in this domain. We'll go through the evolution of cybersecurity from static to dynamic defenses. We'll talk about AI-powered systems, and then we'll talk about how AI is used in defense, such as EDR and threat intelligence, as well as offensive innovations like polymorphic malware and automated phishing. And then finally, we'll address the ethical and governance issues that complicate widespread AI deployment and review emerging research frontiers such as explainable AI and federated learning. And then by the end, you'll have a good understanding of AI's role in fortifying and threatening digital security landscapes. Okay, to begin, our problem statement lies with AI. While empowering defenders with automation and deep insights, it also simultaneously equips attackers with powerful tools to scale and personalize their assaults. This dual-use nature challenges the efficacy of traditional security models, which rely heavily on static signatures and predefined rules. Moreover, a vast number of organizations, especially small and medium enterprises, lack the resources and skilled personnel to effectively integrate AI into their security operations. This disparity risks widening the cybersecurity gap, creating soft targets that sophisticated actors can't exploit. In response to these challenges, this study sets forth 5 major research objectives. These include examining the technical underpinnings of AI in cybersecurity, assessing its operational impact, documenting adversarial applications, dissecting ethical and legal challenges, and spotlighting emerging research paths. These contributions aim to create a holistic, actionable understanding of AI's transformative and at times perilous role in digital security. So first we'll start with the background. So understanding AI's current impact on cybersecurity requires tracing its evolution from early days of network protection. Initially, defenses focused on access control and signature-based systems that flag known malware. While adequate for basic threats, these static models couldn't adapt to emerging unknown attack types like zero-day exploits. As attackers evolved their tactics, cybersecurity practitioners began exploring machine learning and anomaly detection. By the mid-2010s, tools powered by AI started appearing in intrusion detection systems, endpoint protection, and spam filtering, though adoption was hindered by computational costs and privacy concerns. Now, with the support of scalable cloud infrastructures and vast telemetry data, AI has become the linchpin in proactive threat mitigation. Core technologies such as deep learning and NLP, which are natural language processing models, power real-time detection and automation, reshaping how security teams identify and respond to adversaries. This backdrop sets the stage for deeper exploration of both AI's benefits and the dangers it introduces. Alright, we'll move on to our first ways AI is used in attack. So first we'll start with intrusion detection and prevention systems, or IDS or IPS. These are no longer static rulebooks that fail in the face of novel threats. AI has radically modernized them. Where traditional systems relied on known signatures and rigid thresholds, modern AI-enhanced systems use machine learning and deep learning to model normal behavior and flag deviations. Unsupervised methods such as clustering and autoencoders now underpin anomaly detection, boosting the ability to detect unknown threats by over 35%. Even more impactful is the move toward context over IDS, which adapts thresholds based on user profiles and working conditions, dramatically reducing the alert noise for security analysts. Equally vital are emerging standards. As AI becomes embedded in these systems, bodies like NIST advocate for consistent evaluation through metrics like detection rates and false positives. Finally, explainable AI adds transparency, letting operators understand the rationale behind AI decisions, fostering both trust and faster intervention. As you can see, NIST pushes standard metrics, the F1 score and detection rate, which aid in evaluation of potential threats. Continuing on to AI and vulnerability assessment and patching. This mainly focuses on reducing exposure through intelligent risk management. So vulnerability assessment has undergone a paradigm shift, evolving from static, periodic scans to continuous AI-powered monitoring. In agile environments where infrastructure can change daily, this shift is not just helpful, it's essential. AI systems now prioritize risks based on live data, integrating threat intelligence from the dark web, CVSS scores, which is the common vulnerability scoring system, which is used to assess the severity of vulnerabilities in computer systems. It gives them a score from 1 to 10 to indicate how easily they can be exploited and the potential impact they can have on the system. So these tools don't just flag vulnerabilities, they predict which are more likely to be exploited, allowing teams to focus on high-risk issues first. Rapid7's research confirms this approach, identifying 10 to 20% of vulnerabilities as disproportionately risky. While fully automated patching is feasible for low-risk environments, most organizations favor a human-in-the-loop model. This ensures balance between speed and caution, especially for mission-critical systems. That said, legacy tech, noisy alerts, and incomplete dependency mapping still challenge automation's reach. Future directions may include knowledge graphs and adaptive retraining to better model complex systems. Right. And now we'll move on to AI and endpoint detection and response, EDR, which goes from signature matching to behavior-centric defense. So EDR has transitioned from reactive antivirus software to AI-powered systems capable of learning, adapting, and responding in near real time. At the core is behavioral analysis. By modeling normal user and system behavior, AI spots deviations that could signal a breach, even in the absence of known malware signatures. One major advancement is in the reducing false positives. Deep learning enables EDR platforms to cut through the noise, ensuring analysts only focus on truly high-risk anomalies. At the same time, AI empowers rapid remediation. Upon detecting high-confidence threats, EDR systems can autonomously isolate machines, terminate processes, and stop malicious communications. These systems aren't static. They continuously ingest telemetry from endpoints and integrate with global threat intelligence to evolve. With adaptive learning loops and autonomous triad capabilities, EDR tools increasingly function as virtual security analysts, scaling response efficiency across enterprise environments. Alright. Okay. Yeah, moving on to AI enhanced threat intelligence. So this mainly involves correlating and acting on threats at machine speed. So threat intelligence is no longer about collecting data, it's about interpreting, correlating, and responding at scale. And AI enables this by automating the ingestion of logs, OSINT, open source intelligence, and dark web intel. Structured indicators such as IPs and hashes are analyzed alongside unstructured sources like threat reports and hacker discussions. At the core of these systems are machine learning and natural language processing models. They extract actionable intelligence from massive volumes of text and event data, identifying both known and novel threats. Equally powerful is AI's ability to correlate indicators across disparate sources, linking endpoint behaviors with network anomalies and external alerts to reveal multi-phase attacks. With integration into SOAR, security, orchestration, automation, and response tools, These AI systems don't just identify threats, they act. Whether isolating a device, blocking a domain, or escalating an alert, AI ensures that responses are timely, relevant, and scalable. This makes threat intelligence a proactive and automated cornerstone of modern cyber defense. Alright, moving on to offensive AI, we'll start with malware and phishing. So here, mainly AI's adversaries will use a generative and adaptive AI tool. So, here to start with polymorphic. AI is not just a tool for defenders, it also has become a formidable weapon for attackers. Generative AI allows for polymorphic malware to change its code structure continuously, defeating static detection methods. These shape-shifting payloads are guided by mutation engines, fine-tuned by machine learning to evade antivirus signatures and behavioral classifiers. On the phishing front, large language models craft highly convincing and personalized messages. They pull data from social media, press releases, and past communications to tailor messages that appear shockingly real. This extends to full phishing kits with cloned websites, even chatbots posing as customer support. Voice and video deepfakes are the latest additions to this arsenal. Attackers can now replicate executives' voices with just seconds of audio, orchestrating scams that have cost companies millions in the past. And these advances necessitate a shift in defensive strategy from signature matching to real-time behavioral detection and robust verification protocols. So here we have it impacts the traditional defenses because static AV fails as malware variants become infinite and behavior shifting because they're constantly changing, so then you have to keep updating antivirus to be able to keep up with all the changes that happen within the malware. Another way that AI is used in offensive situations is through adaptive attacks and real-time evasion. These are usually dynamic threats that are powered by adversarial AI. So as AI became more prominent in cybersecurity, attackers have adapted by weaponizing its very principles. Adaptive attacks now use reinforcement learning to refine intrusion attempts, reducing failed probes and identifying paths of least resistance. These AI agents evolve their behavior in real time, making detection significantly harder. Malware has become sandbox aware. It detects analysis environments and either lies dormant or alters its behavior to avoid detection. Even more insidious are adversarial attacks on AI itself. Carefully crafted inputs that deceive machine learning models or poisoning techniques that corrupt training data over time. To counter these sophisticated threats, defenders are adopting advanced strategies like adversarial training, ensemble detection models, and robust monitoring of the entire machine learning lifecycle. This ongoing arms race between AI attackers and defenders underscores the need for constant vigilance and innovation in the cyber domain. So we move on to the advantages of AI overall in cybersecurity space. These main advantages are speed, scalability, and situational awareness. But the most significant strength is its ability to scale. So AI is able to process massive volumes of data in real time and surfaces only what matters. Modern enterprises generate terabytes of telemetry data. AI allows organizations to distill this information into actionable insights instantly. A major pain point for traditional systems has been false positives. AI-powered tools trained on rich behavioral and contextual datasets can dramatically reduce unnecessary alerts, freeing analysts to focus on high-impact threats. Equally important is AI's adaptability. It retrains itself using new threat indicators, thereby staying current without needing human-driven rule updates. From enhancing visibility to enabling cloud-native defense operations, AI has become the cornerstone of intelligent, automated, and responsive cybersecurity. Let's move on to the challenges and limitations of AI. So there are technical, operational, and strategic barriers that prevent AI from being used to its full extent. So one of the main challenges is the data quality. Models trained on outdated, incomplete, or biased data can misclassify threats and overlook critical anomalies. making them dangerous as well as ineffective. And there's also transparency. Deep learning models, while accurate, are notoriously opaque. This lack of explainability can hinder audits, slow down incident investigations, and reduce trust in automated actions. Adversaries also target AI systems themselves, launching evasion and poisoning attacks to trick models or degrade their performance. Moreover, not every organization has the means to implement AI effectively. SMBs often lack the technical and human resources, creating cybersecurity asymmetries across the industries. Finally, if not carefully calibrated, AI can produce too many alerts, many of them noise, overwhelming analysts, and delaying response to critical incidents, which can be an issue if the system is actually under attack and they're just they're looking at things that aren't the main problems, which can delay which, as I said, delays response and fixing of these issues. Next, we'll move on to the ethical implications of AI. So AI is mainly, it's all about the surveillance, consent, and autonomy of AI, and how it affects human, and what it has an effects on humans, on civil liberties and human rights. So as AI systems monitor behaviors, scan communication, and trigger automated responses, they can also intrude on user privacy, often without explicit consent or oversight. Transparency becomes paramount. Many users are unaware of the extent to which the data is analyzed or the logic behind decisions that impact their digital access. This lack of visibility raises critical concerns around autonomy, fairness, and trust. Moreover, accountability is unclear when AI takes action, such as locking accounts or isolating systems. If these actions prove unjustified, who is to blame? The developer, the operator, or the model? That becomes the main question. Ethical AI frameworks demand that we integrate principles like fairness, privacy, and explainability from their earliest design stages to avoid these dilemmas. Bias and discrimination further complicate the picture because poorly designed models can reinforce social inequalities, underscoring the urgent need for inclusive, ethics-aware system development. Alright. And here we have governments and regulation, which bridges the gap between innovation and oversight. So while AI is reshaping cybersecurity at an unprecedented pace, regulatory frameworks are struggling to keep up. Laws designed for slower-moving technologies fail to address the speed, scale, and opacity of AI-enabled security systems. The GDPR, which is the General Data Protection Regulation, is a European Union law that governs how organizations within and outside the EU handle the personal data of EU residents. So this has set enforcement precedents by mandating user rights and explainability, yet many jurisdictions lack equivalent protections. Crucial questions about accountability, especially when AI acts independently, remain largely unanswered. Who bears responsibility when a model fails or causes harm? This is a big question regarding governance and regulation. So within organizations, ethical oversight mechanisms like internal review boards or algorithmic audits are often inconsistently applied. Meanwhile, cyber attacks respect no borders. Without coordinated global policies, gaps in one country's governance can be exploited across others. Stronger international cooperation, sector-specific standards, and enforceable AI governance protocols are urgently needed to ensure responsible innovation without compromising human rights or security resilience. And then move on to emerging research directions and the future of AI defense. So the research landscape for AI and cybersecurity is dynamic and rapidly evolving. One of the most pressing areas is explainable AI, which seeks to open the black box of deep learning to make decisions audible and transparent. An essential capability is in high-stake environments. Federated learning offers a privacy-preserving approach to collaborative threat models. It enables organizations to train models on local data while benefiting from shared global patterns without ever exchanging sensitive raw inputs. Other cutting-edge efforts include multi-agent reinforcement learning, where distinct AI agents defend different nodes of a network in a coordinated manner, and continually learning, which allows systems to adapt incrementally without retraining from scratch. Finally, robustness is emerging as a central concern. Adversarial AI, poisoning attacks, and evasion tactics necessitate new architectures and training methods that secure the very models we rely on. These future directions are not just promising, they are imperative to keep pace with evolving cyber threats. So for my conclusion, as AI is fundamentally reshaped both defensive and offensive dynamics in cybersecurity, it enables unprecedented detection and response capabilities, while also arming threat actors with adaptive and scalable attack tools. This dual nature requires organizations to approach AI adoption with both enthusiasm and caution. Key recommendations include prioritizing transparency and ethical design. AI systems must be explainable, especially when they impact critical systems or user rights. Cross-sector collaboration, such as federated learning and shared intelligence frameworks, is essential for building a more resilient defense landscape. Equally important is addressing the talent gap. The growing complexity of AI systems demands professionals who understand both domains. Finally, future-proofing cybersecurity means investing in adversarial-resistant architectures and continual learning. With coordinated action, AI can be harnessed not just to detect threats, but to outpace and maneuver them. And that is all for my presentation. Thank you for listening.